So remember, there's an area down at the very tip of the photomultiplier tube called a photocathode. Photocathodes are typically made out of cesium antimony, and they convert light to electrons, and then those electrons are amplified. And who remembers what the name is of the device that amplifies them? Close. They're called dinodes. Yeah, remember, there's anywhere from 10 to 12 dinodes, and each time an electron hits the dynode, it knocks off more electrons, and those more electrons are accelerated to the next dynode where they, knock off more. It's kind of like there was an old AT&T commercial, where you call a friend and they call their friends, and pretty soon everybody in the whole United States is using AT&T. You guys remember that commercial? It's kind of like an avalanche effect. So one of the things, if we have 10 dinodes, then typically one electron is amplified about 1,000,000 times. Okay. From there, the electrons go to a device called a preamplifier. A preamplifier does nothing more than makes sure that a very small voltage is able to travel through all of the wires and get to your main console. Okay. Some of you may have real fancy stereo systems at home that have preamplifiers on it. Basically, this doesn't change the voltage at all. It just makes sure that there's enough force to get it all the way through the wires to overcome the resistance. Okay. Anytime you amplify something, like over here in this type of an amplifier, you're either you're increasing or decreasing the voltage. But over here, this just sort of maintains the voltage. And then over here in the resistor matrix, okay, this is where we actually start calculating the position that the radiation struck the crystal. Okay? So you notice that there's a positive X, a minus X, positive Y, negative Y. It's in the old days where we had analog computers. Basically, you would add or subtract the voltages from there, and then that voltage would go to the ratio circuit. So basically, if I had 10 positive volts and 2 negative volts, 10 minus 2 equals 8. So that 8 volts would be my X position signal over here that would go into the CRT. Or in this case, you can imagine this as being your computer. The same thing for the Y. There's actually two circuits that you need to be concerned about. One is what we call the positional circuits, which is your X and Y position. I think I told you before, basically your gamma camera is set up like a coordinate system, and so if radiation... You get a question?
Is that the resistor network, or is that
this is actually where the resistor network starts. Okay, let's give a hypothetical example here so that you'll get an idea. We know that 1 keV will produce approximately 1 millivolt. Okay, so 140 keV will produce approximately 140 millivolts. There's a proportionality there. Let's just say that we have a photon that strikes here. Okay, every PM tube in your crystal will see the light from that one photon. Okay, obviously the ones that are right underneath it are going to get a brighter light and produce a stronger signal, but even the ones that are like way over here, no matter where it is on the crystal, we'll see this. The newer gamma cameras have anywhere from about 81 to 125 PM tubes. But typically, we can change the voltage output from PM tubes. I can either make it a positive or I can make it a negative voltage that comes out. So any photon that's striking in this coordinate here, this is going to be both positive. Everything here is going to be a positive impulse. Everything down here is going to be negative. Okay? And then everything in between here, this is going to be both positive and negative. Just by the nature of the beast. Okay? So obviously the radiation striking here, we would take a look at the resistor matrix. Okay, now the voltage coming out of each one of these PM tubes is going to come into this resistor matrix. Okay, and so I'm going to make this one X, minus X, Y, and minus Y. So when all of these signals come out, we're going to say that we get, let's get 70 millivolts positive X, 30 millivolts, let's make it less than that. Let's make it 10 millivolts minus X, 60 millivolts positive Y, and so we've got 800, and then 10 millivolts negative Y. Okay? So this is what came into our resistor matrix. The actual calculation of where the position is takes place in that thing called a ratio circuit. That's a little bit further on. Okay? But this is the information that's going to go to the ratio circuit. And you notice that because that's such a small voltage, we do send it through an amplifier. But in the ratio circuit, then what's going to happen is this. Okay. Now, this information may be digitized before it is sent off. So in other words, inside your gamma camera, you may have a device that will automatically turn this into a digital pulse. Okay. If this was an analog, older gamma camera, basically I would have 70 volts, or 70 millivolts minus 10 millivolts. So over here in the ratio circuit, my X output would be 60 millivolts. Okay? And then my Y would be 50 millivolts. But if we have a digital camera, then that means that we have an analog to digital conversion before it goes to the computer. So what may happen then is I may get the number 7 here, and the number 1 here, number 6 here, and the number 1 here. Okay? And then when this goes to the ratio circuit, then again, basically the computer is going to subtract that. So my X signal will be 6, and my Y signal will be 5. Now in a computer, you have to remember that it's set up as a bunch of intersections. Okay? It's kind of like a Thomas guide, if any of you guys still have maps. I don't think anybody uses maps anymore, do they? Everyone uses GPS on their phones or something else. And again, these numbers can be positive or negative. Okay, so what we're going to assume is, I should put a few more in here, guys. Imagine that this is the face of your detector, and it's been artificially, it has a template put on it that has broken up into addresses. So right here in the center, this is going to be 0, 0. Okay? One thing about computers is we have chips in there, right? Silicon chips. And the silicon chips are designed to store information so long as the voltage is being supplied to them. In your computer you have RAM, right?
Yeah.
Okay. In nuclear medicine, we acquire information in what we call frame mode. I don't know if you've had an opportunity to read chapter 4 with Dan Steves, but I sent you a little thing that goes with it. Okay, so basically what happens is this. Okay, anytime we send a voltage pulse through silicon, it has the capability of storing it, like a little capacitor. Okay, and if I constantly refresh that by continuously sending pulses through it, then that charge remains and the computer knows that there's information there. Okay? Computers read information as either there's stored voltage or no voltage, or what we call 1 and zeros, binary counting. Okay? But here's the problem. If I send voltage all the way down this line, now everywhere where these intersections are, there's like a little RAM memory here that would store that information. Okay? So if this is position, let's make this position, okay, so we have x6, so I need 1, 2, 3, 4, 5. I need to get drawing lessons, don't I?
So it's like graphing on an X and Y kind of deal, right? Like 6 on the right and 5 on the top, and you find the center?
Yeah.
Okay.
Let me see if I can just do this a little bit better. I try to draw this thing while I'm looking at it on the screen here, I get carried away. It's really quite interesting how they do this. Because you want to send a voltage pulse so you can identify where the position is, but if you send, there's what they call a threshold voltage, where if you surpass the threshold voltage, that actually activates that little memory area. So, in other words, let's say that it takes a minimum of 1 millivolt to activate an area on the computer. And if I want to store something in this position here, obviously if I sent 1 millivolt down in this direction, that would activate all of these addresses along the way, and the computer wouldn't know where the data was. Y'all agree?
Yeah.
So what we do is this. When we're sending that information to the computer, we divide this voltage in half. So I send half a millivolt down the X and half a millivolt down the Y. And so if I wanted to get something here, I would send half a millivolt down this address line and half a millivolt down this line. And when they both meet, they'll have enough voltage to trigger and store that information in this spot. Does that make sense? So if I want position number 6 and position number 5 for my X and Y, so my X was 6 and my Y was 5, so I go, 1, 2, 3, 4, 5. So here's X6, and then 1, 2, 3, 4, 5 up here. Okay, if I send half a millivolt down here and half a millivolt down here, when they meet, they're going to activate the memory in this area, and that's where the computer knows that the data was located or where it was struck on your crystal. Does that make sense? Okay. That's basically in a nutshell how it works. They're not going to ask you how to do this, but with digital computers or with digital imaging systems, this is basically how it works. We have these address wires that carry the data, and when the two information pulses intersect, that's where the data is located. One of the examples that I like to use is, let's say that I wanted to get a secret message to Ashley up there. Okay, let's say you have a classroom full of students. Okay, And let's say that here's Ashley. And I want to give her the message, you got an A. But I don't want the other students to know her grade. Okay? So I tell this student in the front row, pass along the information A. So they're going to turn to Ashley, they're going to give it to her, and then Ashley's going to turn around and give it to this student, and then this one. So all the people in this row know is the letter A. Okay? Tell the people in this row, you got an. Okay? So they tell it to that person, and that person. And so basically, by dividing the communication in half, I'm not telling these people anything, but the one person where they both intersect gets the message, and that's how the computer works. Okay? Does that make is that a better analogy? Okay. So, that's how the digital systems work. And that's basically what happens in the ratio circuits. Okay. The other one that's very important, this addition, it's also called a summation circuit. Okay. Now, in the addition and summation circuit, if you remember before, I said the positive X had 60 millivolts, negative X had minus 10 millivolts, positive Y had 50 millivolts, and negative Y had minus 10, oh wait a minute, did I screw that up?
No, you got it right.
Or was this 70?
No, it was 60.
Was it 60 or 70? It was 70.
70.
Yeah.
Y plus was 60.
And this was 60. Okay. Now, if this was, let's say that this was indium, for example, all of these numbers would be doubled. Because what happens is, all of the energy, remember I told you, one of the things that we really try to do with our crystal is make sure that all of the light is detected by your photomultiplier too. Because that's the total energy of the photon that was absorbed by the crystal. And we want to be able to turn that to a number, so when I tell my gamma camera I only want to look at indium, I don't want to look at technetium, it can look at the energy that was produced in the crystal and eliminate everything else. Does that make sense? So when you guys have a, we call it a pulse height analyzer, okay? But what happens is this, okay? In the addition or summation circuit, all of the voltages are added together regardless of their sign. So in other words, we're taking the absolute value. So I add this, and this, and this, and this, and I get 140 millivolts. Okay? If it was indium, this would be 140, 20, 120, and 20, so it'd be like 280. Okay? I'm just going to use the hypothetical. I'm going to give indium an energy of 280 for right now. Okay? So I'm going to say that indium, we're going to make it 280, and I'm going to make thallium 70. So it's exactly half of this, and this is, of course, our technetium. So 140 keV photon is converted to 140 millivolts. That means that if indium was converted, it would produce 280 millivolts. And if thallium was converted, it would produce 70 millivolts. Okay? So, when we add it all together, okay, that creates what we call the Z-pulse. Okay? When you guys tell your gamma camera to stop after 500,000 counts, this is what it's counting. But the secret is this. The X and Y pulses and the Z pulse all have to arrive at the same time in your computer for that event to be detected. Does that make sense? Because if you get X and Y information coming in, but there's no Z-pulse, that data is not recorded. Okay, so all three of these have to arrive at the same time. The Z-pulse is sometimes called the gate pulse because it opens up the door and lets the X and Y information be recorded on your computer. Okay, but before that happens though, I mean actually this Z-pulse should go down here because the pulse height selector actually will only allow a certain voltage through that gate. Okay, that's why we call it a window. Okay, imagine that you have a window that's this big, and if it's at the correct height, you can look through it and see that beautiful tree out there where you guys would rather be right now than sitting in class. Okay? But what if you were too tall? Or what if you were too short? Okay, obviously you can't look out that window, can you? So you have to have an ability to adjust this window so that you can look up here or go down here. So if you imagine that this is my 140 keV and this is my 280 keV and this is my 70 keV, this is one of the things that you do when you change photon energies or change radionuclides. Okay? Plus, we can also increase the width of this window, can't we? Normally, if you're just looking through a little tiny slit in the window, you're not going to see very much. But if I can open that up, okay, let's, like we said, 20%. If you imagine that this is 140 volts here, and that's all the pulse height analyzer is going to let go through this device. In other words, this pulse height selector is only going to allow 14 volts to go through, irregardless. Okay? But you guys have a device up here called an amplifier. Okay? What do you think I would need to do to allow my 280 volt person to look through that window? Let's assume this, okay? I have 140 millivolts that's come into my summation circuit. So here's my X, Y, minus Y. And in order for it to get detected, okay, this is my pulse height analyzer, and it has a little window slit at 14 volts. Okay, so you can look through that window at 14 volts. Back here for just a sec. So now all of a sudden I get something that comes in that's 280 volts. Oh, let me go back over here. Summation circuit, and then we have the amplifier. Okay? And let's say that the amplifier multiplies this by a factor of 1,000. Okay, so 140 millivolts multiplied, that should be what, 10,000? Be points 1, 2, 3, and 40, right? So if I multiply this by a factor of 10,000, that would raise that to 14 volts, right? Okay, so this is my amplifier here. So right now, anything coming to this amplifier is going to be multiplied by a factor of 10,000. So now we got 0.000140 volt being amplified to 14 volts. And as such, that's going to be allowed to travel through the pulse height analyzer Because remember, the pulse height analyzer is going to only accept stuff coming through the window, and it's going to reject everything above it or below it. Okay? So that means that if a photon of 280 keV came in, and it was amplified by a factor of 1,000, that would be 28 volts, and it would be way up here and be rejected. If it was 70, then it would come out and it would be 7 volts, and that would also be rejected. Agree? Okay? So, this is how we handle the problem when we change radionuclide settings. Okay? Let's pretend that the indium, we want to now image indium, so we change the collimator, and now I've got that coming in. So what could I do to make sure that this 280 millivolts is going to be converted into 14 volts? Huh? Well, how about if I just decrease the amplification? Don't you guys have the ability on your radio to turn the volume up and down? So, yeah, if I cut the amplification in half, okay, now this 280 millivolts is going to be converted into 14 volts. Okay, if I had 70 millivolts coming in, what would I do?
20,000.
I would increase the amplification to 20,000. So you have when you guys push a button, what you're doing is changing the amplification for each radionuclide that you want to look at, so that it will go through that 14 volt pulse height analyzer. Yeah. Does that make sense now? Okay. Now, then, the thing is, you also put a window on there, right? Of 20%. Now what we're doing is we're allowing, before we said we had 14 volts here, so 140 keV is converted to 14 volts. What is the window, if I have a 20% window, what voltages would I allow, or what energies would I allow to come in? Okay, well, the way we calculate it, here's your 20% window. Well, that's going to be 28. So 140 times that is 28. So it's going to be plus or minus 14. And we take that number, divide it in half. So basically 154 to 126 keV is what you're allowing. But in actuality, with your pulse height analyzer, you're allowing 15.4 volts to 12.6 volts to come in. Okay. Does that make sense now? A little bit better? No? Yes? Okay. Again, very important, because all you really have to understand is that the pulse height analyzer is where you reject those scattered photons. Remember, when the radiation is interacting with atoms in the patient's body or electrons in the patient's body, the energy is reduced. So we can't accept that because it came from some other part of the body. Sometimes two photons will strike very close, and the light from both of those may be perceived as a higher energy photon. So we don't want to lose that information either. So we're willing to accept a little bit of more energy than, we know technetium only has 140 keV, but if you have two light photons that hit close together, okay, so this was 140 and this was 140, your gamma camera may assume that that was one 280 volt pulse, or if it gets partial energy from one of these, I can add that to the 14 volts here, and that event will be recorded, so I don't lose everything completely. Does that sort of make sense? But like I said, the thing that you have to keep in mind is that all these components are definitely potential questions that you'll see. So the ratio circuit establishes the location, the pulse height selector establishes the energy of the photon, and as I said before, this is what you count when you're going for a certain number of counts. Okay? So you're counting Z pulses. And the Z pulse, when I say blanking over here, okay, normally this blocks any information from being recorded, but the Z pulse comes over here and it unblanks this, and it allows the X and Y information to be recorded so long as they all arrive at the same time, within a few milliseconds of each other. Okay? So far, so good, huh? But this is what we were talking about here now. Some of the other devices that we have in here, okay, so we know the resistor matrix. I put this device in here, a pulse shaper. When the electrical pulses are coming in, it helps, let the computer know that there's not like 2 or 3 things added together. So the pulse shaper basically prevents what they call overriding of the pulses. It's like if you were at the ocean, if you ever see, okay, you have one wave that's this big and then another one this big. Okay. So they're arriving at about the same time, but sometimes you'll have one wave that catches up to the other wave and then they're both added together, and then that's going to be obviously rejected. So pulse shaper just makes sure that stuff doesn't get, distorted when it's sent to the gamma camera. Okay. And then the linear amplifier, remember the linear amplifier is often the device. The 2 ways that they allow your gamma camera to identify radionuclides, I can either change the voltage in the linear amplifier, or I can change the voltage in the photomultiplier tubes. Okay, remember I told you that the photomultiplier tubes have 100 volts potential difference? But if I'm doing 140 keV, I'm using that 100 volts. But if I go to 70 volts, then I can increase the diode voltage to 200. I can double the voltage there. Or if I'm using 280, I can decrease the voltage to 50. So in other words, I can either vary the voltage that I'm using to knock electrons off in the diodes, or I can just have a linear amplifier that allows me to change the voltage in the main amplifier.
So it can be technically done at
PM tubes.
full PM tube, okay.
Yeah. Most of the times they don't do that. PM tubes are real sensitive little creatures. I don't know anybody that does that anymore. Most of the people, you just use the linear amplifier. And actually what normally in modern gamma cameras, when you push the button, the gamma camera electronics will automatically sense for the peak. Does that make sense? So in other words, if you had, so here's our 201 thallium at 70, here's 99 technetium at 140, and here's 111 indium at 280. When you push the selector button for that, the amplifier will automatically adjust and find that peak, because that's your highest voltage pulse. Remember, this is called the photo peak because what type of interaction has occurred? Yeah, photoelectric absorption. So all of the energy of the photon was absorbed by the crystal. Okay? So when you change radionuclide setting, this is what's actually happening now, is we're either increasing or decreasing the amplification until that peak is under the window. Okay. Okay, now, so the next thing we want to be concerned with is quality control. Next week, I'm going to give you a little quiz over just these components, the 11 components that I have listed here. Probably give you a diagram like this and have you identify what component does what part. So,
There are a couple components that are here that are not up there, so.
well, which ones?
For one, there was light pipes.
Oh, that's a good point, yeah, a very good point there. Okay, remember we talked a little bit about how the thickness of the column, or the crystal affects sensitivity and resolution. Okay, so here we have 2 sodium iodide crystals. When the radiation comes in and it's absorbed by a thick crystal, now this one may be maybe a ½ inch thick. Just so you know, we use 5-inch thick crystals, sodium iodide crystals, for PET detectors. Because you have to stop that high energy radiation. Okay. When you have a thinner crystal, the light doesn't flash around all over the place as much. So this would be for high resolution, and this would be sensitivity. And remember that sensitivity and resolution are inversely related to each other. Okay? So this one is going to detect more counts. This one's going to give you a sharper picture. So what they tried to do was, in order to increase the resolution on this, remember the light's going off in all different directions. But if I put a little piece of glass up here, kind of like a little fiber optic piece of glass, then that means that all that light spreading around, it'll still spread around, but only the stuff that's almost directly underneath this light flash will be allowed to continue up the light pipe and go to the PM tube. So light guides or light pipes are designed to help improve resolution. And they look like little test tubes. They're like little pieces of glass. They're all, they can either be thick or thin, depending upon if they want high resolution, they'll make very thin glass light guides. If they want to have, kind of a more uniform looking picture, they'll put thicker ones. Okay? Now the problem over here with this guy, the high resolution, you get a nice picture, but you don't get as many counts, and it also shows up defects in the crystal. Mainly because, thin crystals are not going to be as uniform as this, as the thicker ones. So because of the fact that this is going to have a very non-uniform appearance, sometimes they put a device in there called a uniformity computer. And the computer is going to divide up the crystal into a matrix. Now, I know that your guys are used to taking images of like 64 by 64 and 128 by 128 and things like that. Typically, the uniformity computer only has a 32 by 32 matrix. They might be a little bit higher, but basically, if you remember, the smaller the matrix, the more statistical information I'm going to accumulate in there, right? So, for example, let's say I have a 2 by 2 matrix here, and 100 photons come in. I would assume that that there's 100 photons. we would assume that approximately 25 would be collected in each one, right? But if I go to a 10 by 10 matrix, okay, now there's more options. I might have one photon in each address, or I might have a two or a couple. So what's going to happen now is this is going to create what we call a grainy or noisy image. Does that make sense? So I might have like 2 here, and 1 here, and 0 here, and 4 here. And so what happens is you get a real kind of a grainy looking image that is more difficult. So that's why whenever we do uniformity correction, or I do spec imaging, we use a larger matrix, because we want to avoid the noisy image or the grainy image and have more uniformity, okay, from low statistics. Do you guys get pretty low statistics when you do a spec heart? Huh? People are shaking their heads, no!
64 by 64 matrix.
Well, I want you to think about this, okay? You injected 25 millicuries of sestinib. Roughly about 4% of it, maybe a little bit more, is in the heart. And you're looking at it for how many seconds on each projection?
More than 25 seconds.
Okay, so if you had, so you have 32 projections, and each one is 20 seconds in duration, 20 to 30 seconds. We'll be generous and make it 30 seconds. And you have a 10,000 count per second count rate, if you're lucky. Actually, that's pretty high. Okay, normally it's going to be a lot lower than that. Huh? I'm being generous here. So basically, you got 30,000 counts here and 30,000 counts here, if you're lucky. Okay, that's not a lot of counts. And that's going to be divided up by 4,096 pixels. So, SPECT imaging is not statistically a very good way to do this. But if you made it longer, then you're only going to be doing like 2 patients a day, right? And so the problem then is, throughput of patients and statistical information. But after you acquire this image, then what you do is to get rid of the graininess in the image. What type of filter do you use? Okay, yeah, to get rid of the graininess, we use a low-pass filter. And basically what that does is it averages. So if I've got 75 here and 50 here and 100 here and 80 here, it's going to average these together. We actually use what they call a 9-point smoothing. Did you know that? Your computer will look at the surrounding 9 pixels. So the one that you're going to change is the one in the center here. But it looks at the top 3, the 2 on either side of it here, and then the 3 on the bottom. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got 9 pixels. All the numbers in there are going to be added together. And then they look at it from every possible combination that you can add these together. There's 36 combinations that you can use. If you look at the vertical, the horizontal, the diagonal, there's 36 possible ways that you can add those things up. The computer does that for you and then gets that average, and that's going to be the new number that goes in here. Then it's going to look at the one that's next to it. It's going to do that for every pixel in your 4096 image. Wow. So that's your low-pass filter. Then we have what they call a high-pass filter. And what does that do?
Leaves the graininess.
Well, we don't want graininess, but what we do want is sharp edges. Okay, so a high-pass filter, it gets rid of what they call the low frequency. Low frequencies are normally produced by large objects. Okay? And remember, what's the process of converting a three-dimensional object into some kind of a signal called? I think I showed you guys last week, didn't I? At some point.